All right. Module 2, the trade terms. I did notice more and more they're pulling questions out of the trade terms. A lot of people miss questions out of trade terms on the first test, not only this class, but a lot of my other classes. So that's just to say, make sure you guys are reading through these trade terms. I would recommend doing flashcards or doing that trade terms quiz in the back. But obviously, like some of these trade terms are super important. Calibrate, calibration, displacement, drift. Drift's going to be an important one. Gradual change of an instrument output from the corrected value. So drift is the reason why you would need to calibrate. See, precision and accuracy. We're going to talk a lot about precision and accuracy today. What the differences are, and then like transmitters and transducers. We'll talk about quite a bit today as well. But all those trade terms, make sure you guys like at least are reading through those. And I would highly recommend reading through those before lectures and stuff, just so you have an idea of what I'm talking about. Most of them, if not all of them, you have heard before from Mr. Wally or somebody in the past. First highlight, page 1. I highlighted the heading of the detector and sensor bullet point, and then that goes along with the last sentence, which has the blue primary element highlighted in the book. So highlight detector or sensor, and then highlight this type of device. It's often used as the primary element or measuring element of the instrumentation channel. So that would be something like this is a big, assume this is a thermocouple. I haven't looked at the wires, but this would be a detector or sensor. This is going to be at the process. We're going to be measuring temperature, probably you change the temperature up or down of the process, but this would be thermocouple would be one example of a detector. Okay. Transducer. I don't have the highlight for transducer, but it converts one form of energy into another form of energy. What's the most common type of transducer in instrumentation? I to P. Good. I to P transducer, which means I have what going in? What does I stand for? For electrical, what does I stand for? Current. Y'all know Ohm's law? Yeah. How many's taken at least through electrical too?
We might need this. I don't.
You should know it by heart. What's Ohm's law? Anybody? What does E stand for? Voltage, I is current, R is. You gotta know it for instrumentation and stuff. So this is the transducer. Transducer, current coming in, current written with an I. P coming out, what does P stand for? Pressure. So pressure coming out. What's our most common instrumentation signal? Milliamps. What specific milliamps? 4 to 20 milliamps coming in. Then output, and a regular output pressure would be like 3 to 15 psi. So that transduces, that changes current to a pressure. Most common type of transducer. So you know, like I talked about pop quizzes and stuff like that, we'll be having a pop quiz today. In the class, we'll be having a pop quiz. So that's on anything I go over today. So just be ready for that. So thermocouples, stuff like that is known as the primary element. Transducer changes from one form to another. And then they're going to talk about each one of these different categories more in depth. So flipping over to page 2 and 3. You guys should have. All right, so pages 2 and 3. They talk about panel review. So this is where you would have your detector or sensor. So remember, detector or sensor, that would be like your thermocouple. It's actually touching the process. What's the range? That detector can go into a transducer. Maybe it's an I to P, right? This is inputting the current and outputs a pressure. That goes to an amplifier. A lot of times I'll talk about these transducers and amplifiers are being put into one device. Back in the day, they had to be other devices, like it'd have to come out of a transducer, be amplified, and then stay in the signal. Now our stuff's getting so good where we can combine devices, transmitter, and then goes to an indicator or receiver. So the indicator would be like somebody's HMI screen or digital dash telling them what it is. This is the review channel that we're going to follow and stuff like that, getting people to not have to mess around and stuff. So say we had a tank of water that we wanted to keep at 100 degrees, right? This thing is inside. This thermocouple is inside the tank telling temperature, right? This is our detector or sensor. This is telling what the temperature inside the tank is. This is going to a transducer. So that transducer is taking, anybody remember what type of signal a thermocouple puts out? Millivolts. Without a millivolt signal, you're thinking of an RTD, resistance temperature detector. Thermocouple will put out a millivolt, so that'll a transducer will change that from like millivolt to something else, right? Whatever you're wanting it to do, and then eventually it's going to transmit down to the controller. So a controller can be a DCS computer. It can be a PLC, that big rack that's up there. It can be, you guys started working on these 2 big blue trainers over here. There's a PID controller. That's a lot of times what it is. It's the brains, right? So thermocouple is telling the brains what the temperature is. This is making a determination on we're at 100. You want to be at 100 degree set point. Say we're at 80 degrees. Not there. So it's going to control the final control element. This can be like any type of like anything that's going to heat the process up. It can be gas burners that kick on and start heating up. It can be just resistance elements inside the water, like anybody replace the elements in their hot water heater? It's just like a coil, 2 big coils in there. It can kick on elements like that. Anything that's going to raise the temperature of that, and then it's going to go back to the process. And this is going to see it. Oh, we're at 90 degrees. Still crank it up. Oh, we're at 102 degrees. Turn it off. Okay? That's the channel that it's going to be in. That is the detector. It's the first thing that's going to, there's the thing that's touching the process. In 111, detector or sensor, I've got a few questions or a few highlights on page 3. Top right of the page, I've got 2 sentences up there highlighted. It's important to realize that a sensing element always extracts some energy from the process. So the process is disturbed to some extent by the act of measurement. This effect is referred to as loading. Loading. So you guys have heard what an orifice plate is, right? Everybody knows what an orifice plate is. You probably heard the word orifice plate 6,000 times. Pressure comes to an orifice plate, hits it, creates pressure, right? Backside, there's less pressure, and the differential pressure gauge is taking the 2 pressures and determining a flow or a level, right? But that pressure is hitting that and creating a head loss. That is loading. You are creating a disturbance to tell a known effect, to tell what the flow or level or something like that is. That's what loading is. It's taking energy out of the system in order to tell a temperature. Loading, very, very, very small, right? I have this in my tank of water. It's going to extract some energy, right? This thing has to heat up. I'm pulling heat out of the system. It's almost irrelevant, right? The amount of heat that this is going to pull out of the system, it's still pulling energy out of the system. It's still considered loading. It's just minimal. An orifice plate is going to take a ton more energy out of the system because that pressure is hitting that plate and causing head pressure loss. That's called loading. Second paragraph, first sentence is highlighted. Detectors are selected for measurement systems based on the parameter being sensed. The desired accuracy, the range of measurement, and the particular type of output supplied. So Obviously, for what you want to measure. Am I going to use a thermocouple to measure level? No, I'm going to get something that's temperature level. And then same thing. You can change what you're using based on, there's certain thermocouples that are really good for like 0 to 200 degrees, but then you get up to like 2,500 degrees, you have to use a different type of thermocouple. You might be like, why don't I just use that thermocouple on all of them? Well, that thermocouple doesn't work well from 0 to 200 degrees. It works well from 1,000 degrees to 2,000 degrees. Plus, it's probably going to be 5 times more expensive. So why would you buy like something way more expensive if you just need to measure 0 to 200 degrees? Different reasons for buying different things, and why you're selecting them. Third paragraph, first sentence is highlighted. Detectors measure process variables such as pressure, temperature, level, and flow. All instrumentation. Pressure, temperature, level, and flow. Reading. I actually like that table 1 does a good job of going through and saying different types of detectors that are used. So temperature, thermocouple is what I got up here on the desk. That would be one for temperature, or an RTD. Kind of the same thing, just has another wire and uses resistance rather than millivolts. Pressure, differential pressure cells are used quite a bit, but you also have a board-on tube. You might know what a board-on tube is. What is it?
Big picture. Fans and contracts with pressure
So where do you use them?
gauges.
Pressure gauges. So if you don't remember this, you can have a pressure gauge that looks like this, right? You got pressure coming in, right? The board-on tube looks something like this, and it's sealed off at the end here, and then the center of this is connected to a dial. So this is where you're like 0 to 100 psi's, right? There's gears and stuff like that in here that make this turn at a certain rate. So whenever I push pressure inside of this board-on tube, this is an enclosed tube inside of this system. When I push pressure inside of here, it tries to straighten out. Like you're putting so much pressure in there, it tries to like straighten out. If I put an insane amount of pressure, that pipe would just straighten out and blow out the end, right? But it's rated to where a certain amount of pressure is put in, and it'll move ever so slightly, and that slight movement makes the dial change. Board-on tube. Okay. Level, we have a differential pressure cell. We've talked about a float. So that's just, anybody opened up the back of their toilet before? You see that you either have like a long arm float that goes up and down, or you have that thing that goes alongside the sleeve that goes up and down. That's a float. All it's doing is shutting off water when it gets to the top of your tank. Very, very basic, but you can get higher and higher degrees of floats and stuff like that. Flipping over to pages 4 and 5, the transducer or converter. 112, the first sentence, 112 is highlighting. The function of a transducer is to convert whatever input signal it receives into another type of output signal that is more suitable for use by the next component or portion of the instrument or control channel. We got we're on page 4, module 2. Skip a sentence, and I've got the whatever sentence that is highlighted. In either case, the output signal from the detector serves as the input signal to the transducer. So, output signal of a thermocouple is usually what? Remember? Millivolt. So my output of my detector goes in to my transducer. The output signal of my detector serves as the input signal of the transducer. I'm saying that because this is a highly asked question on this test. Output signal of this is the input to my transducer. Where I have I to P right here, it would be, what's the letter for voltage? E. Does anybody know why E is voltage? If you think of voltage more as a pressure and a force, at least it helps me understand what it is. But this would be an E over P. Some people still say P, but it's usually E. All right, amplifier, signal conditioner. Just remember, this is an older book. I don't see amplifiers that much anymore. Or I haven't seen them in a while. But my highlight for this is the second paragraph of 113 last sentence. For this reason, it is likely that amplification is performed at some point in the channel, even if the instrument channel block does not include an amplifier block. It's the last sentence of the second paragraph. So that's just saying, if you don't see an amplifier, it's probably being performed somewhere else. Transmitters, 114. Transmitter block, first paragraph, second to last sentence on page 5. Many modern smart transmitters include a detector, a transducing element, amplifiers, and a signal conditioning noise filtering element. Many modern transmitters include a detector, transducing element, amplifiers, and a signal conditioning noise filtering element. So that's saying everything is in one, right? Out to the side of that, you need to write there's no calibration standard for transmitters. You don't calibrate a transmitter. Right? All they're doing is taking in the signal and sending it out. No primary calibration standard for transmitters. All right, review of terminology. So this is stuff you've seen before. 121 accuracy. First sentence in 121 at the top is highlighted. Accuracy is the degree to which the output of an instrument approaches with an accepted standard or true value. I'm going to give you these highlights and I'm going to talk about precision versus accuracy. So that's accuracy. Go down to 122 at the bottom of the page. First sentence is one of the highlights. Precision of an instrument is a measure of its repeatability or consistency. So precision is an instrument is a measure of its repeatability or consistency. The rest of the paragraph is a separate highlight. A detector or sensor with a high precision should continually output the same value if the component being measured does not change. However, precision does not necessarily mean that the instrument is accurate. It could be consistently outputting an inaccurate result. So, has anybody ever done target practice, shoot guns, bow and arrows, anything like that? Right? So I got a big target right here. Bullseye right here. If I'm shooting at that bullseye, that's my grouping. Am I precise? Yes. Am I accurate? No. Right? If I hit here one time, I'm accurate. Right? It's what it's wanted to be. This is accurate. This would be precise. All right? A lot of times with these pieces of instrumentation, they're going to be precise, but they're going to be off a little bit because they're not calibrated right. Right? So that way, if they're not accurate, we have to calibrate. If it's kind of a troubleshooting step. If they're not precise in something, or if they're not accurate and not precise, and I'm hitting stuff all over the place, something else is wrong. right? You kind of have to use this as a little bit of a troubleshooting technique. Like I am constantly 5 PSI off of my gauge, my super calibrated gauge that I'm reading in my hand. Well, I'm gonna have to recalibrate that device. It is precise, right? If you have something that's not precise, then you're gonna have to dig in a little bit more. Stuff like that. But you need to know the difference between accuracy and precise. First full sentence on page 6 is highlighted. Accuracy is the measure of how close the result is to the accepted standard value. If I have a set point of 100 degrees Fahrenheit for my water tank, that is the accepted standard value. If I'm off of that, it's off accuracy a little bit. I'm at 99 degrees and I'm 1 degree off accuracy. Measurement errors, 1, 2, 3, first sentence is highlighted. A measurement error is the numerical difference between the measured value and the true value. So, measurement error is just how far off we are from our bullseye. Okay? There's stuff you can get into measurement error like almost to a fault. So where I said like you can buy different pieces of equipment depending on how like strict you want to be with your tolerances. So you can have, say we want to be at 100 degrees Fahrenheit. Well, some places it doesn't really matter if we're at like 70 degrees Fahrenheit or 103 degrees Fahrenheit. It doesn't really matter, right? With some pieces of the devices, like we have to be at 100% on 100 degrees Fahrenheit. Well, then they can take that down and go like between going from like 97 to 103, they can take it down to 100 and do like 99.5 to 100.5 and like get tighter and tighter to where you're like 100.005. Like the tighter you go, the more expensive stuff is going to be. So you're always going to have error, right? You're not going to be 100.00000 degrees Fahrenheit, right? So you're always going to have a little bit of error, and your controller, based on how tight your tolerances are going to try to hit that 100 degrees dead on. But it's always going to be looking at that error, trying to go up or down based on that, depending on how tight your tolerances are. All right, flipping over to page 6, reproducibility and drift. First sentence of 124 is highlighted. One, two, four, reproducibility is the degree of closeness with which the same value can be measured at different times. Next paragraph, first sentence is highlighted. Drift is a gradual separation of the measured value from the calibrated value. You get that a lot with scales. A lot of times I would have to go calibrate a scale at least once a night or every other night. Scale, like really capacitance scales have a lot of drift, or at least the ones that I've been around doing. Next paragraph on the right-hand side of the page, last paragraph in that section, first sentence. Drift is the primary cause for the need to recalibrate instruments. Drift is the primary cause for the need to recalibrate instruments. Sensitivity and responsiveness. This is kind of what I talked about just a second ago. First sentence on page 9 is highlighted. The engineer selects a sensitivity based on the smallest change needed to be measured in the given process variable. Right? So if we have our big tank at 100 degrees, and I have those elements in it, let me just kind of draw on this a little bit. Big tank filled with water. We got our thermocouple right here. We want to keep it at 100 degrees Fahrenheit. So we want to select our stuff based on the smallest amount of change needed. If this is just a hot water, let's say this is a hot water heater, right? Most of the time you can crank hot water heaters up to about 120 degrees, something like that. But hot water heaters don't keep stuff dead on 120 degrees. Like it'll go, anybody ever notice if somebody uses water in your house, like hot water in their house, take a shower, and you take a shower immediately after them, it's hotter than normal? That's because like that hot water controller will actually raise this above 120 degrees and then shut off. Okay, so that's not a very sensitive device, but who cares if your hot water's 3 degrees hotter than it's supposed to be, right? Doesn't really matter. But say I had, instead of, it would be super accurate. Let's say instead of temperature, we're measuring level, right? Level of water in a tank. Water's not expensive. Doesn't matter if it's 3 feet off, right? Doesn't matter. Think about if you're working for a company that makes cologne or perfume. How much difference is there in 3 feet of cologne or perfume? How much money is that? Right? You can get a little bottle of cologne for like $60 plus, whatever. It has to be way more precise. That's all I'm trying to say. Is like sometimes it doesn't matter if you're off. Sometimes it does. So you select based on that. If you have to get more and more precise, what does that correlate to? Cost is going to go up, up, up. And usually stuff that has to be more calibrated more frequently, the more precise you are. So engineers select sensitivity based on the smallest change. Standards and elements of measurement, direct versus inferred measurements. If I remember this stuff from instrumentation 2. Down at the bottom of page 9, last sentence in the second to last paragraph, last 2 sentences. Human senses are not sensitive enough to detect measurements such as pressure, temperature, and flow in a quantitative way. To measure these variables, a more complex measurement system is used. Out to the side of that, write inferred measurement. I'm going to give you the next highlight that I'm going to talk about. Pretty much the entire next paragraph is highlighted as a separate highlight. Inferred measurement occurs when there's an indirect comparison. That is a change in the process. Variable affects a characteristic or property of the material, the measuring system or detector. It's a change in the detector that's actually being measured. For example, when a certain temperature exists in the junction of a thermocouple, a voltage is produced. A voltage is the actual parameter being measured, and the temperature is inferred or derived from the characteristic of that voltage. So what they're saying is like humans can't measure temperature, pressure, flow, temperature, pressure, and flow. We can measure level, right? We can directly measure level. Like if the tank has a level inside of a tank like this, I get a tape measure and go like that. That is a direct measurement. Okay. Also, anybody ever seen the big tanks fill up gas tanks at a filling station where they check their level? Yeah, wood dipstick. Like it looks super unconventional, but they stick that dipstick in there and pull it up, and wherever it is on the dipstick, that is a direct measurement. It is this deep, right? Anybody stick their hand in Mississippi and tell how fast it's flowing? Nope. Anybody know the exact temperature of this room by doing this? This is where we have to take an inferred measurement, right? Those are inferred measurements. So we stick this inside of our tank, 100 degrees, right? What is this measuring? Voltage. The voltage of this changes, and based on that voltage, we can determine the temperature. So that is an inferred measurement. This is sensing voltage. How much voltage this determines, or how much voltage this has. We have charts and tables and computers and stuff like that that can determine a temperature based on that, right? We can have deflector plates that you can put in a body of water that's flowing. However much pressure is being pushed on that deflector plate, it can tell a flow. What am I measuring? Pressure. I'm taking pressure and I'm determining a flow. Anytime you're taking one form of energy and converting it to another, it's an inferred. But where you can take like a tape measure and I can measure the length of this desk, that's direct. Anytime you have to go from one to the other, It's inferred. Differential pressure transmitter, orifice plate, right? High side, it's on the front side of that orifice plate, low side. What am I detecting? Change in pressure to determine a flow, pressure to flow, inferred measurement. I know that if I have 100 pounds of pressure on this side and 50 pounds of pressure on this side, I know that it's this amount of flow through this size pipe in these calculations. Inferred measurement. 132 measurement standards, right in the middle of that paragraph where you got NIST. In the United States, the ultimate set of standards is maintained by the National Institute of Standards and Technology. All of our meters and stuff like that, devices, calibration tools, you open up the back, there should be a sticker, and everything gets calibrated back to a specific standard. So everything goes back to that as long as your stuff, your tools are calibrated. Nothing else highlighted on pages 10 and 11. Flipping over to page 12, 137, calibration. Second sentence of 137, third sentence is highlighted. The procedure for establishing and adjusting an instrument's accuracy is called calibration. The procedure for establishing and adjusting an instrument's accuracy is called calibration. The immediate next sentence is a separate highlight. Calibration tests the validity of an instrument's measurements in normal operation. Off to the side of that one, right, compare the known value. Compares to known values. So what that means, like calibrating, like I talked about calibrating the scale. Just going to use my experience as necessary. So where I worked in the steel mill, we had big coils of steel, right? So how we calibrated this scale was we took all the weight off of it. Then we hit, there were buttons on the back of this. You got a 0 and span. Took all the weight off, push the 0 button. That's just like your little cooking scales and stuff like that. It zeroes it out. Then whenever this plant was started up, they had a junk coil that they couldn't sell. They welded it all together and they got a weight on it and it was an exact weight. I think these usually weighed about 35,000 pounds, right? Something like that. It was something like super exact, like 35,286 or something super exact. Take all the weight off, hit 0, put that known weight on. I hit span and there was something in here that says like, what's your span weight? I put that in and it calibrates everything in between 0 and 30, whatever I said, 280. It calibrates everything in between to that standard. There's no coil I'm going to put on this scale that's going to be heavier than this. And there's no coil that's going to be lighter than 0, right? So that's calibration. You have your known value is whatever you're putting on that scale. You can also do this. You can also do it with, we'll talk about where you can do it with different pieces of meters and stuff like that, where something might get a 4 to 20 milliamp signal. We have process meters that you can bump up and like it can go from 0 or from 4 to 20 milliamps and output that and simulate a signal, but it's a known signal.
Proofing tanks too.
What's that?
You used to use like proofing tanks for flow to calibrate meters. So it's a tank that's graduated. Fluid through it into the tank. Compare the graduation on the tank to the meter.
It was a known value, right? Like
Yeah.
you knew how much was in that tank.
Yeah.
So you could see it was an open top.
It
Or you
had
could
a
see
gauge. It
had
had
a
a sight
gauge on the
gauge
side.
on the side.
Side gauge on the side. So
Yeah.
that's a known value that you can calibrate to. Right.
We have to take the temperature of the product.
Right, because you have to
Go to API chart.
apply for specific gravity and stuff like that. But yeah. Take a couple minutes and do those 3 questions on page 13. soon as those guys get back, we'll start back up. All right, let's run through these. Number one, the detector, sensor, and the typical instrument and process control channels, also known as the primary element. D. Two, the degree to which the output of an instrument approaches an accepted standard or true value is known as accuracy. And three, procedure for establishing and adjusting the instrument's accuracy is called calibration. Any questions on those? I'm gonna go into this second section. It's long. So just hang with me. Through this stuff, they talk about a ton of different types of detection. So this is section 2 of module 2. All right, section 2, going through trade terms. The electromagnetic field. So this is important for everybody to know. So pretend this is the end of a wire, right? Wire comes straight out of this board, right? Electromagnetic field. That is a field that this puts off, electronic field. It's invisible, that you can't see. It is based on the amount of voltage and current going through that wire. Whenever you use the BP pin that beeps whenever you have voltage, that's how this works. If I have a BP pin and I get within that field, that pin can sense that, it starts beeping, the light turns on, right? The reason that this is so important is because of induced voltages, right? Whenever I say induced voltages, I mean that if I put another wire right here, this wire is inducing voltage onto that wire. Okay? That means that it's changing the voltage of this wire minimally, and it's all based on what the insulation is, the thermoplastic wrap is, the amount of voltage, the amount of current, but it is inducing a field on that wire, right? What's our most common signal in instrumentation? 4 to 20 milliamps. If I got a big high power cable right here and a 4 to 20 milliamp cable right here, what's going to happen? It's going to jack my signal up. Like I got a big power cable right here and it's inducing voltage on this. My signal's not going to be accurate. That's why, like instrumentation 1 and 2, y'all learned like you can't run power cables and instrumentation lines together. Like those raceways and stuff like that have those channels in the middle. You should learn about, like, you have to separate your instrumentation cables and your power cables because you will induce a voltage. Everything that has current flowing through it has an electromagnetic field, EMF. Laminar flow is going to will be important for a lot of pieces of detectors and stuff like that. I think we talked last week about glow valves, right? Yeah, we did. Glow valves on the back end of glow valve has high head loss. It does a lot of turns inside that glow valve. So on the back side of that glow valve, my flows and stuff are very turbulent. And if I put a detector over there, most times detectors want real laminar flow. So you either have to put a flow straightener in, or like that detector will say like you have to go like a certain amount of parts past the valve to get straight flow. And it's usually like 8 feet or something like that. But all of it has it in the manual. Like if you have a glow valve or something like that, it's going to create turbulent flow. Either put a flow straightener in or go this distance away. Magnetic lines of picofarad. Farad, you just need to know that's how capacitance is measured. Piezoelectric, it talks about quite a bit. My first highlights in the first paragraph on page 14, third sentence. A detector is the first system element that responds quantitatively to the measured variable and performs the initial measurement operation. So that's like your thermocouple, your pressure transducer, stuff like that. The first thing, primary element. Temperature detection, 210, 211, bimetallic strip thermometers. First 3 sentences are highlighted. A bimetal element, figure 10, is comprised of 2 different metals bonded together. One is usually copper or brass. The other is a special metal called invar, which contains 36% nickel. These aren't super common anymore. These used to be thermostats in everybody's house, right? You have thermostats like this, or you have the mercury ones. But essentially what it does, what happens to metal as you heat it up? It expands, right? Do all metals expand at the same rate? No. So if we put 2 dissimilar metals, and one expands, say this bottom one expands way more than the top one, it's going to expand and keep trying to go. Well, they're stuck together. Well, it's going to cause it to curl, right? This metal, whatever this isn't going to expand as much. So it's going to start curling because this metal on the bottom is trying to expand, right? So it can literally expand and makes these contacts not touch together anymore. So this could be anything. This could be contacts to start up a heater element or something like that. And when you put heat close to it, it separates them so that heater element turns off. This gets cold again, it touches the contacts, that heater element turns back on. That's a very crude way of talking about it, but that is a bimetallic strip. I think they use these quite a bit in, the next picture kind of shows like the old school, and I don't have it up here, but if you look at that picture in the top right of page 15, like these were mercury thermostat. Anybody still got a mercury thermostat you know of? Anybody ever pull the cover off of their thermostat and see like the liquid metal in there? These are old. I don't know if they're illegal or not anymore, but mercury People get mercury poisoning, cause you go crazy, stuff like that. I talked about that last class. But that mercury can cause a connection. But that bimetallic strip bends to where that mercury will either make the contact or not. Top left of 15-second sentence. The spiral wound element is the most compact in construction and is widely used in thermostatic switches. So this is the top left of page 15, second sentence. The spiral wound element is the most compact in construction and is widely used in thermostatic switches. Thermocouples 212. Thermocouple, first sentence. Thermocouple is a detector that can directly convert the difference in temperature into an electrical energy. What's the electrical energy? Millivolts. Millivolts. I always think it's crazy. This isn't a highlight, but right after that, first thermocouple was formed in 1821. That's nuts. They're using millivolts in 1821. And they figured out that two dissimilar metals welded together can create a millivolt signal based on temperature. Makes you feel dumb. 16. They can have, I don't have highlights on these, but they have I don't have any highlights on pages 16 and 17, but you can see they have the helical bimetallic strip. This just gets more movement, right? Like if that strip is just coiled around this, the more it heats up, the more the shaft is going to spin the difference in temperature, right? So this is like, if you have like a food thermometer, putting in your grilling and stuff like that, that's how these things are working. It's a bimetallic strip inside of that. If it's not electric, like it doesn't have batteries in it. If it's bad, anybody have like a battery powered thermometer for doing cooking meat or anything like that? My dad does. That's a thermocouple. That's all it is. But if you're doing just if you don't have any, it's just like a prick point, not hooked up to anything. That's a bimetallic helical temperature gauge. Flipping over to page 18, designations for thermocouple wire. All thermocouple wire is color coded. My highlight is in the first paragraph, last 2 sentences, 1 sentence. To make this task easier, the International Society of Automation, ISA, has developed standard MC96-1 temperature measurement thermocouples to establish uniformity in the designation of thermocouple wire. Going along with this highlight is the sentence in the top right of the page. Top right of the page says, for thermocouples and thermocouple extension wires, the color red designates the negative wire. Top right, page 18. For thermocouples and thermocouple extension wires, color red designates the negative. That's for all thermocouples. You need to remember that. Those two highlights go together. If you want to put an arrow or something in between them, they just ISA created the standard. Red is negative. Bottom left of page 18, last sentence down there. The manufacturers of thermocouples also use color coding to designate both the type and polarity of thermocouples and thermocouple extension wires. Bottom left of 18, last sentence in the bottom left. The manufacturers of thermocouples also use color coding to designate both the type and polarity of the thermocouples and thermocouple extension wires. So on page 19, you can see that that graph. I talked about this graph right here. I talked about thermocouples and stuff that you would use for certain temperatures and stuff. So you look at the bottom, temperature ranges. I just know from experience, the three most common that I've messed with thermocouples in that are J, K, and R. All right, J and K are pretty similar because they have similar ranges, right? They're both pretty good from 0 to over 1,000, and their rates, the voltage increases steadily with the temperature, right? All thermocouples, your temperature or your voltage increases steadily with this. But if I'm going to like a type R, like if I want to get up to like 1,500 degrees, I can't use a J or K. I have to use an R or an S or a B. Did I go with that? So that's just the amount of millivolts that these different types put out based on the temperatures. Page 20, pressure detection. Feel like it's going into all the stuff that I've already talked about. And their picture looks just a little bit better than my picture. Two highlights that I'll talk about. 221, first two sentences are highlighted. One device that uses displacement distance to measure pressure is the board-on tube. In this case, however, it is the device itself that displaces. Key in on that. That's one of the higher missed questions on the test. It's the device itself that displaces. Most of the time, like my thermocouple, is this going to change physically? No, it's just changing like the temperature and changing the flow through this. With a board-on tube, this actually moves and changes. It physically changes. Second paragraph, last sentence, last two sentences. The material of the tube is selected based for its elastic properties. It deforms under pressure, then returns to its original shape when pressure is removed. So all like the metal that this is made out of is determined based on your pressure. Like obviously lower pressure stuff, like for your car is actually pretty low pressure, right? Like most people are putting 30 to, you drive a heavy duty truck, like I put 70 to 80 pounds in my tires, but then like that's low pressure. So that's where you can use like maybe a thinner walled tubing, going to be cheaper. But like I said, pressure pushes into this, it's wanting to go straight, right? The more pressure I push in this, the more this thing wants to straighten out. So this moves, changes this gearing, and the needle will change. Pressure gauge, right? Everybody go with that? That's a board-on pressure tube inside of a pressure gauge. Diaphragm pressure gauge, 222. Last paragraph on page 21, first sentence. The distortion of the diaphragm under pressure is transmitted to the gauge dial by a linkage connected to the center of the diaphragm. This is a diaphragm. So this is like some type of rubber material or something like that. And this pressure pushes on that. And based on that movement right there, it changes the dial. If I go with that, fairly simple. The diaphragm is some type of rubber, but it's as that diaphragm moves, the gauge moves. It's usually pretty small movements. Pressure capsules, 223 on page 22. First sentence is highlighted. Technology commonly used to measure low pressure is a pressure capsule. Low pressure capsule. So you can tell this is pressure capsules. This is metal, right? These are just bulbs in metal. So this is a very low amount of pressure. You think about how little that's going to move. Pressure capsules are for very low accurate pressure measurements. Same paragraph, right after where you see 4 to 20 milliamp, I got a sentence highlighted. A pressure gauge or transducer incorporating the pressure capsules typically used with lower pressures. They can fall in the range of 0 to 30 psi-G. Pressure gauge or transducer incorporating a pressure capsule is typically used with lower pressures that fall in the range of 0 to 30 psi-G. Bellows pressure device, 224. Second paragraph, first sentence. The bellows type pressure gauge is usually built as a one-piece, collapsible, seamless metal metallic unit with deep bolts formed with very thin-walled tubing. And the last sentence on the page is also highlighted. In practice, the bellows is always opposed by a spring, and the deflection characteristics of the unit are a net result of the bellows and the spring. The net result of the bellows and the spring. How that put it.
The bellows.
Remember what this is?
Built.
And I bring this in here for chapter 1. Anybody remember what this is called? Goes on the front of the valve. Position, good. And I think I opened it up and showed you all the bellows that's inside of this. I'm sure you did. Maybe not. Here is instrumentation for it. So this gold piece on the inside of this is that. It is just a metal thing that has that can move. Like I'm not gonna move it a lot, but very small amount of pressure makes it move back and forth. And then it's opposed by a spring. I don't know if y'all can see it, but there's a spring right beside it. So it's the combination of the bellows and the spring for this to determine like where the valve needs to go. So this uses a bellows pressure capsule or a bellows pressure device. I'm not gonna pass it around. Look at that here in a minute again. Always the net, the bellows, and the spring. Level detection. This is going to get. Anybody know what a capacitor is made out of? How do you make capacitors? Should learn that a capacitor is two plates separated by a dielectric. So a lot of times you'll have this whole thing will be a capacitor, and I'll have like so be plate 1, this is plate 2, dielectric. I don't know how to spell it. Dielectric in between, right? So the capacitance is based on how close the plates are together. All right, that's all it is. So it can determine a charge based on how close the plates are together. So if I'm using this as a pressure sensor, all that means is if I had a scale and I had this underneath it and I step on it, my pressure is pushing right here. It's pushing these plates together, and then the capacitance is measured in what? Farads. Usually micro or pico farads is usually, it's very minimal. Is how you measure capacitance. So the more pressure I push on this, the closer those plates are together, and it determines a capacitance that we can change into a pressure or a weight, right? So is this an inferred or a direct measurement? Inferred, because I'm measuring pressure, outputting a capacitance to determine a weight or a pressure. Kind of weird. I guess I'm measuring capacitance to determine a pressure. But it's how close those plates are together changes the capacitance. Okay, nothing is highlighted in 2.5, but I need you to know that for level detection. So we're going into level detection. First thing is we're doing capacitance type level detectors. First sentence is highlighted. The answer to my question earlier. The capacitors consist of two conductors separated by an insulator. Two plates separated by a dielectric. Flipping over to page 24. I'm going to give you these highlights and then I'll talk about them. Got two highlights from 24 and 25. Second paragraph right above the did you know? First two sentences are highlighted. A bare metal probe is used to measure the level of non-conductive liquid. The probe serves as one plate of the capacitor, while the tank walls serve as the other. And then the other highlight I have is on page 25. Second to last paragraph on the left-hand side. Second to last sentence. The most commonly chosen insulating material is PTFE, which is called Teflon, which has a dielectric constant 2. All right, so let's talk about how those work. So capacitor is what? Two plates separated by a dielectric, right? It can be in the form of like a disc, or we can turn our whole tank into a capacitor. All right. So the first thing was we were determining a pressure based on capacitance by putting pressure and getting those plates closer together, right? We have two different plates. One plate will be the wall of the tank, and the other plate is the probe that we put in the middle. Do we change the size of our tank walls? Nope. Do we change the size of our probe? Nope. So what's changing? The level of dielectric. Good. So I'm not moving my plates closer together. I'm not pushing pressure on them, but that dielectric is what's changing. And based on the amount of dielectric we have in our tank, it'll change the capacitance. And based on that capacitance, we're going to determine a level. Does that make sense? You're turning the whole thing into a capacitor, the whole tank. And this is that's with a non-conductive liquid that you can use the tank walls with a metal probe. Non-conductive. So the dielectric is what's changing the capacitance to determine the level. The second one is if you have a conductive load or conductive material as your dielectric, you just have to insulate the probe. With what? Teflon. Yeah. Does that make sense? Turning your whole tank into a capacitor. Usually, I think they're talking there. Flip over to page 26. The third paragraph on page 26. Right in the middle of that paragraph, I have a highlight. As previously shown in table 5, the dielectric constant of water varies greatly with temperature. This can be compensated for through the use of an RTD or thermistor as an other input to the measurement system. Both of these devices react linearly to changes in temperature. Michael, this is probably what you were talking about. Like you had to know the temperature of the tank. That's what this resistor is down here or down here. That's our RTD that's measuring the temperature of the tank. And based on that temperature, it can put like a fudge factor in the controller. And it can that controller can see I have this capacitance with this temperature, and then output us the exact level. So temperature can affect your readings. But if you have like water, it's highly the capacitance is highly affected by temperature. So you throw in not a fudge factor, but you're taking the temperature to do a correction factor. I think that's what compensation factors. Ultrasonic level measurement. My highlight for this is the last thing on page 27. Secondly, and more significantly, the velocity of sound varies with temperature, atmospheric conditions, and the composition of the liquid. Since measurements accuracy depends on knowing the actual sound velocity, ultrasonic level detection is suitable only for installations where those conditions are relatively constant. Mostly, ultrasonic is going to be in an enclosed tank, right? Ultrasonic, everybody's going to be messing with ultrasonics, especially on the bigger trainer, like the 4 of y'all started last week. That's I think the last lab is messing with the ultrasonic, and there's just one. Like the emitter receiver is in one unit down there. If you ever done a tour back here, I always talk about ultrasonics because usually the high school kids. Everybody know how bats see at night? They use ultrasonic waves, like they put out little chirps or beeps or whatever, and then how fast that sound travels back to them. They can see how far away they are from something. That's the exact same way that these work. They send sound waves down to the level of the liquid, and they bounce back up, and based on that amount of time, they can determine the level. Right? So these are used a lot in closed tanks. They're not used in open tanks because stuff can get in them. The more this bounces around, the more this reading bounces around and stuff like that. So they're just saying the conditions have to be pretty particular for these to use. But I saw these are used everywhere, like any kind of closed storage tank and stuff like that. They work very well. They're easy to work with. 233, nuclear level detection. I've never messed with nuclear. That's not true. We did have a Geiger motor too. X-ray components. I'm gonna give you the highlights of these. There's 3 separate highlights that are all one question. Right after the caution on page 28, first sentence is highlighted. Nuclear level detectors generally take 1 of 3 forms. The simplest and oldest is the Geiger molar tube. A lot of times if you're sensing for like nuclear radiation stuff, you'll hear somebody say like the Geiger tester or something like that. That's in movies like where they're walking around and that thing starts screeching. That's a Geiger tester. The next paragraph, first sentence is highlighted. The second type of detector uses a long tube called an ion chamber, mounted parallel to the tank wall. So you got the Geiger molar tube, the ion chamber, and then lastly, up at the top right of the page, first sentence up there, the third type of detector is called a scintillant counter. It contains a chemical that emits flashes of light when gamma rays strike it. So if you're looking to ask about nuclear level detection, you got the Geiger molar, the ion tube, and the scintillant counter. Blow detection, orifice plates, 241. Third sentence, the orifice plates usually mounted between 2 flanges. Please don't miss that one. 241, third sentence, the orifice plate is usually mounted between 2 flanges. Everybody fairly familiar? I feel like orifice plates talk about more than anything. The whole program. You got a plate with a hole in it, creates a differential pressure. You can turn the flow based on that. Flipping on to page 30 and 31. Page 31, second paragraph, first sentence is highlighted. Orifice plates are the most widely used the primary flow elements because they are inexpensive and easy to install. All it is a plate of metal, super accurate holes punched out. Second paragraph on 31, first sentence. Orifice plates are the most widely used of primary flow elements because they are inexpensive and easy to install. Venturi tubes, 242. First sentence. When properly calibrated, the Venturi tube is the most accurate of all primary elements. When properly calibrated, the Venturi tube is the most accurate of all primary elements. Next paragraph. Fourth sentence is highlighted. The low pressure is measured in the center of the cylindrical throat. So orifice plates. This is the side cut out of an orifice plate. So my orifice plate is sitting right here, right? Pressure is coming this way. It's this orifice plate. What side's my high pressure side? This side. So you can see high pressure. So this is measuring high pressure. It's the other side of the plate, and that's my low pressure side. Now my DP plugs into those, subtracts the difference in pressure, and determines the flow based on that. Right? So just the 2 different sides of the orifice plate. Venturi tube, your high pressure tap is all the way right here, and your low pressure tap is at the center of the cylindrical throat. You don't really see the Venturi tube. Everybody saw the Venturi tube that was out there when they're going through this stuff. It's just a block. It doesn't show the shape of the actual thing. It has a block so it can hold that pressure in and stuff. But this is a Venturi tube is like this, right? And it's the most what? Accurate. You're also not going to have a lot of loading, or as much loading as an orifice plate. What's loading? That head loss or turbulent flow, right? This flow, say it's water, it's going to flow a lot smoother through this than it is just hitting that orifice plate and being kind of dead end, right? Smooth transition. Center of the cylindrical throat. Flipping over to page 32 and 33. I don't have highlights on these. But there might be some questions. Pitot tube, we got one out there that you're gonna work with, closer to the end. It just has two different, you have a high pressure side and a low pressure side coming out of one tap. So the high pressure is a smaller, opening than the low pressure. I don't have anything to say much about those. Magnetic flow meters, 2-4. I don't have any highlights in 32 and 33. Magnetic flow meters, flipping over to page 34. My highlight is in the middle of that third paragraph. The process, it's right in the middle of the third paragraph on page 34. The process fluid is the moving electrical conductor. So they talk about the right-hand rule, left-hand rule, but pretty much this is a magnet, and you have to have some type of conductive liquid. Is water conductive? Yes. If you're standing in water with your bare feet and you throw a cord on the ground, you're gonna get shocked. Conductive. It's gonna pass electricity through it. So say you have water flowing through this, it's conductive. It's inducing a field on this coil, and based on that electrical field, we can determine a flow. What's a big advantage to using a magnetic flow meter? No head loss. Exactly. What's another one? I shouldn't have to shut down the plant to change it out. Everything is mounted external to the pipe. What's the downside, you would guess? If it's not conductive, you can't use it, right? Can't use it on the air. Can't use it on the air. They're insanely expensive. Orifice plate's gonna cost less than $100. Magnetic flow meter is gonna be like $10,000. So where do you want to use them? Stuff like that. Like, yes, this is great, but they're $10,000. It goes through the math on how to calculate all this stuff. I've never had that on a test. It's never been on a test, so I don't go over it. So I'm stopping the lecture right there. You go ahead and stop.